Welcome to the multivariable calculus section. In this section, we'll be discussing arc length and curvature. So recall from the beginning of multivariable calculus that we have our vector function, which is f of t, g of t. Additionally, recall that in single variable calculus, we had the following formula in order to derive our arc length. So it was L is equal to the integral of BA square root 1 plus dy dx squared dx, and of course we can rewrite this in terms of dy, but that was the general formula that we used. So now in multivariable calculus we're going to be using x equals f of t, y equals g of t, and now because we're dealing with curvature we're going to say z equals h of t. So we remember from the beginning of parametric curves that L is equal to the integral of from a to b of the square root of f prime of t squared plus g prime of t squared dt. So now that in 3 dimensions we can incorporate the last component and state that L is equal to f prime of t squared plus g prime of t squared plus h prime of t squared. And additionally, this can be rewritten and most commonly written as b of a and the magnitude of r prime of t dt. So that would give us the arc length of our form. But curvature, now curvature is a little bit different. So curvature is denoted by this funky looking K. It's just very odd looking, and it is given by the dt over ds. And this has a plethora of applications because dt is not bound to a single value and ds isn't bound to a single value. This means that our curvature is also equal to the magnitude of the t vector t prime over r prime of t, as well as the magnitude of r prime of t cross r double prime of t over r prime of t cubed. And that is a bunch of information, but that is the arc length and curvature broken down into the conceptual aspects, and I hope that helps.